Well, hello friends. Welcome back to the program. Today, we are going to work on hash tables. So we've had this hash table data structure in Serenity forever, and it is not the most efficient data structure. It has a good API, but internally, it is implemented in a very inefficient way. So the way it's done is that it allocates a table of buckets, and then items are found by first hashing the key that we're looking for, and then we just find the bucket that matches the hash. So let me see. You can see it right here. Essentially, it's just hash modulo the capacity. That's how we find the bucket index, and then the buckets are each a singly linked list of t. So essentially, you have something like, let's see, a hash table of string is actually a something like this, right? And then this thing is allocated like this. And then when we have a hash to find a bucket, we do mbuckets hash capacity. But the thing here is that this is horrendously inefficient because of the use of singly linked list. Singly linked list is a very simple data structure that allocates every time you append to it, it allocates a new node. So if we look at singly linked list, how it's implemented, we can see here that there is a struct node that has the t value and a pointer to the next element in the list. And when you append an item to the singly linked list, we do a new node. And likewise, when you remove something from the list, we will delete that node. So there's a heck of a lot of malloc and free traffic incurred by the singly linked list template, and of course then also by the hash table template. So anyway, this is something that has annoyed me forever, but I never actually sat down to implement a better hash table, because I was always like, well, it works, and no need to mess with it right now since it works. But today we're actually going to invest the time in building a better hash table. So the hash table I have in mind is instead of having the buckets be each a singly linked list, we would do this thing called closed hashing. I think that's what it's called. And basically, we want to put the values in the buckets directly. So instead of having buckets be like this, we would have something more like a struct bucket that is, I guess, we know if it's used or not, and then we would have a t for the value, and of course we don't want to actually construct anything unless it's used, so this would have to be something more like values storage size of t, something like that. And then we also need to keep track of deleted items. And then the thing is that we would just have the buckets be mbuckets is new bucket capacity. So that part is fine. But then when we do a lookup, instead of finding a list, because I guess the thing I didn't mention about these lists is that once you find the bucket list, you have to actually iterate through the elements in the list until you find what you're looking for. Because if you have hash collisions, which are, not uncommon, that means that we put more than one item in the same bucket. So then you have to traverse that list to find the actual item that you're looking for. So in this new data structure, we'll have this thing here, but there won't be a singly linked list to traverse at the bucket. So if we find a bucket that is used, but we do an equality check, and this is not the value that we're looking for because it does not do, it's not equal to the thing we're looking for, then we have to like look somewhere else. So then we'll do a second hash. So we'll like rehash the hash that we had, feeding the hash back into the hash function, giving us a new number, and then using that as the next bucket. So there will be like a sort of a linked list in this table that uses the hash of the hash as the next pointer. That's sort of the basic idea. And I hope you understand what I mean. Anyway, I'm just gonna start writing this data structure. So I guess either we could like update the existing one, or I can just like write out a new one. It might be easier to just write out a new one, and then we can port the new one to the API. So we'll call it like the that mash table. I don't know, something like that. And then let's see how we would do this. So this goes in the ACK namespace, of course. And let me just see what template params we had here. We really just care about the value type and the traits type. So yeah, template type name, let's call this the value type, or yeah, T is fine. Traits for T, hash table. All right. And then we'll come up with our bucket. I guess we can put that here. Or you know what, let's put it here. And it will have used false, deleted false, and storage for the value. Size of T. Types H. Okay. So that looks pretty good. And then we'll have a bucket and buckets. And we'll want to track the count. Again, this is the number of elements in the hash table at the moment. The capacity is the total size of the bucket table. And then we'll also need to track the deleted count, because when you delete something in a hash table of this type, then because it participates in a linked list with the hash of the hash, we can't just break that chain when we delete something. So instead of like breaking the chain and then making it impossible to find any subsequent items in that chain, we just mark something as deleted, because then when we iterate, then we know to skip over it. And then I think we can probably like reuse deleted slots if you insert something and it would fit the deleted slot. But I don't know, we'll get to all that stuff. So let's see. So we'll do some basic starter items here. So rehash with capacity. Okay, so what does the rehash do? A rehash is basically what we want to do when we can no longer fit, like we want to insert something and we can't fit it. So we have to actually widen the bucket table and then take all the stuff from the old table and put it in the right place in the new table. So let's see how we would do that. Or actually, let's write out some other code first. So let's see here. Manage table. Okay, so clear. How do we clear this? If there are no buckets allocated, then there's nothing to do. Otherwise, we have to, let's see, this thing could use a typecasting thingy. So I'll call this like slot. Something like this. Storage. Yeah. Then the issue here is that for deleted or unused buckets, we don't want to default construct T, because T might be something, we might not want to default construct it, right? So here, to clear the table, what we want to do is just iterate across all the buckets. And then if a given bucket is used, so if m buckets, if m buckets I used, then we delete it. And then at the very end, we can just free the buckets. So in ACK, we usually use camalloc and kfree. I'm not exactly sure why we started doing that. I think it's just to have like something that works both in the kernel and in user space, but it's a bit weird. But we'll do it with malloc and free, because then we don't have to think so much about construction and destruction of these things. We'll do that manually. I think that'll be easier, actually. So capacity becomes 0, size 0, and deleted count becomes 0. Everything becomes 0 at the end. Even the buckets. Okay. And then if you want to find something in one of these, so or let's insert something, actually. So set result, or what should this thing return? We have some type for that in the, yeah, hash set result, right? So we'll call that yeah, we can just reuse this, actually. That's fine. Set, and then we have a tamp. Okay. And now we want to move this thing into the table at its correct position, and then we want to return whether it was a new insertion or a replacement of an existing entry. Okay. So this would look something like ideally, we would find a bucket, so like lookup for writing value, and then bucket slot. We would just do a move construct here, so t move value, something like that. And then we'll also update used true, bucket deleted is false. Okay. That seems good. And maybe we'll have a convenience overload here. So return set t value. Okay. And then lookup for writing. That's, yeah, we're gonna put some logic in there. So how would that work? So that thing needs to always succeed, right? Because you should always find somewhere to insert. So that will be a bucket amp lookup for writing. And we take the const reference here, right? Because we're not moving it anywhere. We're just finding it right place. So let's see. Actually, maybe we should have a lookup for reading that's easier to implement. So we'll do that one first. So it'll be a const. And how do we find the right place? Well, we start by hashing the thing. So hash is traits, hash value. And then, wait, in the hash table, don't we have a default argument for the traits? Traits for T. I guess we don't normally instantiate hash tables so much. We are using them through hash map. So here, hash table type in hash map is hash table entry traits, and entry traits are the custom traits used. Okay. So just looking how that was done. So yeah. So the traits type is what we use to control how comparison and hashing is done for a given type. Because if you want to, you can override the comparison function. For example, if you wanted to have a hash table of strings, but you want the hash table to be case insensitive, then you can still just put any string in there and then just override, implement your custom traits and have the traits ignore case in the equality comparison function. That's how you would do that. So that's pretty nifty. Anyway. We actually have something for that right here. And as you can see here, it's not very efficient. It will convert to lowercase, both for the hash and for the equality check. So huge opportunity for improvement there, the case insensitive string hash traits thingy. Anyway, so lookup for reading. So we hash the value, and then I guess we'll find the bucket index will be hash modulo capacity. Okay, so that's where we start searching. And then bucket is mbuckets at the bucket index. Okay, so this is where we start looking. And if it is used, let's see. So if it's a deleted bucket, then we have to skip to the next one. So that's a, oh wait, no. The last thing we'll do. So how do we skip to the next one? To skip to the next one, we have to compute a new hash, which will be int hash of hash, I think. That's what we'll do. Let's get that. Hash functions, yeah. So we'll rehash the hash to find the new location, And then bucket index becomes, again, hash modulo capacity. So because the inhash function is quite good at moving the bits around, eventually it will cover every possible index, and it should be reasonably good at that. So yeah, this is our linked list of buckets, basically. So let's see. So if bucket is used and traits for t equals value, if these are equal, so bucket slot, then it's a match. Then that's our bucket. Return the bucket. Right. So what constitutes the end of the list, right? That's interesting. So the end of the bucket list is when you're looking for something and you keep rehashing until you hit something, you hit a bucket that's not used, not deleted, and that's the end of the list, I guess. So it's not used and not deleted. Deleted, then we didn't find any. Okay, cool. So then looking up for writing is, let's see, look up for reading. So we can start by doing this. So if we have this thing already in one of the buckets, then we should just write back to the same bucket. So we can just return that bucket here. It's a little bit goofy, but I think, yeah, we'll just do it this way. This is not the most efficient way of doing this. We could combine the lookups, but we'll start by doing them separately. So let's see. Right, but if we don't find it, that means that we have to insert it anew. So how do we do that? Well, we need to make sure that there's space for it. So if I guess the used bucket count plus 1 is greater than the capacity, then we need to rehash size plus 1, let's say. And then the used bucket count is the number of deleted plus the number of used items. So yeah, there we go. I don't know if we even need to expose the capacity of a hash table. I will think about that later. Okay, so rehash, and then once we have rehashed, then we want to do a lookup again. So essentially this logic here, it's just that we're looking for a place we can insert something new. So we're looking for the first hit, which is unused, and deleted is fine. So hash is traits for t hash value. Right, and then so we'll start here, and then if bucket is not used, wait, if it's not used, then we can just use it, I guess. Return bucket. that's cool. And then otherwise we will just rehash, move forward. Yeah, I think that's good. And so, of course, you'll notice now that we have this interesting thing that the capacity, if you fill the hash table, then the linked list will go on forever, right? Because you need to have like an extra slot where the list can end, because otherwise we won't have a logical conclusion to the list. So we need to like maintain a capacity that's slightly greater than the number of items at all times. And I don't exactly know what's a great number for that. So for now, let's just let's make that decision in rehash. So if capacity is, let's say capacity is max of capacity and 16. So we don't want to be smaller than 16. That would be very small. Or how about we let 4 be the smallest? Also, what's up with that? Why can't I do that? All right. And then we want to make sure that we wait, where do I want to do this? I want to double things up somewhere, so I'm just going to double things up here. Yeah, we could probably tune this later to get better performance, but right now let's just do size plus 1 times 2, just so we grow the table to accommodate the list structure within. Okay, so now what do we want to do? We want to allocate a new buckets. So that would be malloc. Oopsie doopsie. Malloc size of bucket times capacity. Or let's see, maybe we should just do it this way. Old buckets is m buckets. Old capacity is m capacity. And this one we'll rename to new capacity. M capacity is the new capacity. Okay, great. And then, and then we iterate all of the old buckets. So let's see, auto bucket in old buckets. If bucket is used, then, wait, we can't iterate like this. We don't know how big that is. Old buckets I. Okay, so if old bucket is used, then set move old bucket slot. Can we just move out like that? I think so. And then we'll want to invoke the destructor on the old bucket slot. So old bucket slot t. And then we need to free the old buckets. I guess if we have old buckets. So if we didn't have any old buckets, we can just leave here. Return And then free old bucket. All right. Let's also mem set. All right. This feels reasonable. You know what would be handy is I was just thinking about iterators, but we'll deal with iterators when we get there, which maybe should be now. So let's see. What did the old iterator type look like? Hash table iterator, the hash table type, element type, and bucket iterator type. Okay, so that makes sense. Type name T, type name, bucket type. Because what is really an iterator into a mash table here? It is a, I mean, it can really just be a bucket pointer if we are clever. So if we just point at a bucket, null putter, bucket type, sorry. And then do we need to default construct these? I don't think so. So the way you would make one, let's say that template, wait, can we just do this? Wait, are they? Okay, I'm gonna cheat. Are they friends here? Friend hash table type. Oh yeah, that's so obvious. I have the hash table type right here. Okay, you're my friend. Great. And then we'll make a private constructor that simply takes a bucket pointer. Thinking, do we need the table for any reason? I guess we can take it just for sanity checks here if we want to. Or, well, maybe we don't need it for anything. We could do some assertions, I guess. Like table. Yeah, let's do that. Let's assert that we're not in the middle of rehash when you're creating an iterator or something, because that would be goofy. Or, you know what? We can come back and do assertions later. We don't need to get all ahead of ourselves here. So we'll just initialize this like this. And then this thing needs to have a operator star. Return m bucket salute. Something like that. And we can also do one of these guys. And of course, the famous operator plus plus. To move forward, which we'll simply call maybe something like skip to next, which we'll put down here. So how do we skip to the next thing when you're iterating? So essentially, the way you would do that is, first thing is we got to null check this. So if we're a null iterator, which will be the end, I guess, then we'll just return. Otherwise, we will do, wait, so we'll move forward plus and bucket. So we go to the next bucket. And then if that bucket is used, and we'll stop there because we found a used bucket. Otherwise, we'll just keep going while the bucket is deleted. Wait, how do we know that we're at the end? We don't know when we get to the end. What if we track that like this? That could work. And then if bucket end, then m bucket is null pointer. But then we have to keep track of end. Well, we can do that. So end will be a special bucket that's past the end. And when we allocate buckets, we will simply sneak in an extra bucket like this. Very, very sneaky. And then m buckets capacity end is true. Yeah, that's good. Okay, I'm just trying to think. Am I considering everything here? So the end bucket is only relevant when we're iterating, because then we're always skipping ahead. But when we're doing normal hash lookups, then we're following the double hash chain, which will never send us to the end bucket, because we're always normalizing to the capacity here with the modulo. So we don't need to care about end in any of these. Yeah, okay, that makes sense. So let's see. So we have set. We should also make a get function. What was the get API? And the old one didn't have a get. Well, we have find. Okay, so we have a find API that takes in, this is an equality comparison callback, and it takes a hash and a finder. Oh, and then find with value is simply a wrapper around find like this. Yeah, we can do it this way. That's very useful, actually. So I guess first we should just bring those iterators in. So we'll say using iterator is hash table iterator. And then it was actually mash table iterator, my bad. Mash table. And we wanted the T and the bucket type. Okay, and then we also need a const iterator, which is the same, except the T is const. And I guess the bucket can be const as well. Okay, I'm gonna peek at how we did that in the old one. Const iterator is const hash table. Okay, all right. Yeah, that seems fine to have everything be const. All right, so how would we go about implementing like begin, for example? So begin would simply be return iterator with a bucket, which would be our very first bucket. But what if it's not used though? So we would need to find the first bucket that is that has something in it. So Wait, what would we want to do here? I mean, we can just iterate through the buckets, actually. If m buckets I is used, then return iterator buckets I, like that. Otherwise, if we don't find it, we'll just return end. Yeah. And end will return an iterator with a null pointer. Okay, and then const iterators will just work the same way. Const iterator begin, right. Does that make sense? Okay, I feel like I want to test this out at this point, so maybe we'll make a test program and see that match table CPP. Yeah, that's fine. Mash table. Actually, why don't we just grab the test hash table, test hash map. Oh, test hash map? Oh, that's a bit annoying. Well, I guess, okay, never mind. I'll just... Let's see, mash table, string, traits. I forget how this works. What are the traits for something? Traits. Something like that. Okay, and then table. We'll just set some of these guys. See what happens. Oh, I need a not equal comparison for iterators. Return. mBucket is not other mBucket. It's a fascinating comparison. Test mash table. Wait, how do I get this thing to build? Wait, what file am I editing? Mash table CPP and act test. Okay, all right. Mash table. All right, we have some problems. Great. So line 154. I forgot to return whether it was a successful replacement or a new insertion. Interesting. So, wait, how do we want to communicate that? I guess. So we'll just do this. So if bucket is used, result is mash set result. Well, actually, we can just do it this way. If it's used, then it's a mash set result replaced. Otherwise, it's a mash set result inserted new entry. And then we had memset of a non-trivial type. Yeah, that's my bad. I guess I cannot have these guys here. Unused result. Yeah, that's true. I never returned it. Okay, so floating point exception. Wow. That's special. Did I divide by 0 somewhere? Lookup for reading. I'm gonna need to have some slightly nicer debugging info here. Let's just max out. Wait, that didn't make it any better. Right, that's different CMake lists. Okay, let me just put that here as well. Oh, wait. Okay, line numbers, finally. So we're doing a set, and we're doing a lookup for writing, and then we're doing a lookup for reading, and then that fails on line 194 because my capacity is presumably 0 at this point, because the table is empty. And when it's empty, there's nothing to be found. That's very silly. All right, look at that. Our output is correct. And it's also in order, which is interesting. Let's see, because it should not necessarily be in order. That's a little bit suspicious. Let's add some more just to see that they would get out of order at some point. Now it loops forever instead. Well, that's also interesting. Lookup for writing is looping. Why are you looping? Let's see. Let's print out something here. So lookup for writing with capacity. Okay, and then we can say what we are visiting. So bucket index used is, yeah, I can print them all out like that. Bucket index, bucket used, bucket deleted, bucket end. Because what happens? Oh. We are looping, and used is true. Wait, so we've filled a table and we didn't expand it when we needed to, it seems like. So I messed that up. Where was the set lookup for writing? if used bucket count of is greater than capacity, but what if it is capacity and we also need to grow? That's not good enough. Okay. Let's see. Hash. New capacity. So rehashing to 2. Okay, so then that gets scaled up to 4 by rehash. But then we should definitely have done another insertion. Oh, wait. Are we not bumping the size when we insert something? I guess that's probably what's happening. We do set. Yeah. M size. And if bucket was deleted, then we need to decrement the deleted count. Yes, here we go. So we're skipping these empty buckets here. Or we're printing them, actually. Let's see. So I think our iterator does not skip buckets correctly. Yeah. So this is the whole table. But we should clearly be skipping these. So why are we not skipping them? Skip to next. If bucket is used, we'll return. So let's see. Wait, does this make sense? Skip to next. We don't. Wait, why do we care if it's deleted? If it's deleted, we want to skip over it, right? If something is used. If something is not used. Wait. Why am I brain blanking on this? Okay, so skipping the iterator next, we go to the next bucket. If that bucket is used, then that's our next bucket. Otherwise, we should continue. So as long as the bucket is either it's deleted, but what if, wait, why does that matter? As long as it's not the end, we should just keep going, no? Yeah. I don't know, why would deleted matter? Because used is the canonical authority on whether there's a value in the storage. Okay, so that's good. Now everything comes out good. The order is jumbled as expected. Great. So let's see. Then what do we want to do next? I guess implement some of those find functions. So what did they look like? Let me grab the API that we had. so we want these essentially straight up. And they would be calling something that is like this. So finder. That's really like a comparator, or it's an equality checker. I guess we can call it finder. That's probably whatever. We don't have a lookup with hash function, so I guess we need one. Outside of that, this also does not work this way, so we would have lookup with hash. That would be like something like this. And then return iterator bucket. So it could actually be like that. Yes. And if we make this thing return null putter for empty, then this would work. Okay, so that's cool. So let's do const version of that. There we go. And then we just need to implement lookup with hash. So how would that work? That would be a bucket lookup with hash, unsigned hash, and a finder, whatever that is. We'll decide that later. I mean, you'll decide that when you pass us a finder. So if it's empty, then return null putter. And it's essentially this code right here, just that we have the hash, right? Lookup with hash. So really it should be like lookup for reading with hash. Well, we can call it lookup with hash. Maybe that's okay. Anyway, instead of calling equals here, we'll call the finder. And do that. And then we can implement this function in terms of the other. So this would just be return lookup with hash, traits for t hash of value, comma, something like return traits for t equals entry value. And here we only need the value by ref. Boom. Okay, that's pretty good. Does that still build? Not quite. Lookup with hash. I'm passing a const foo as this. Yeah, that's true actually. Well, whatever, that's not difficult to fix. So this could be a const bucket actually. It's probably, or that will break later. Yeah. We'll deal with that later. Just get my backup tea. Okay, so this still works, and now we can implement something like contains maybe. So that would be contains find value is not end, right? Contains let's see. So we should get a true, and then we should get a false. Nice. That's very nice. Okay. So let's look at what other APIs we had over here. Oh, these are used for the assertions that I talked about, right? So like the hash table knows if it's currently clearing or rehashing itself. Yeah. We have remove with iterator. That one we're going to have to implement. Right. So how would we do that in the mash table? Remove with an iterator. Where's that implemented? Here. Okay. And remove with a value, just finds the value and then removes it like that. Yeah, okay. So we'll copy this interface. So what the old code was doing to remove was it would just, so it would find the bucket and the iterator contained a bucket iterator. Oh, that was a very confusing data structure. The iterators, as they currently exist in the tree, the hash table iterators, they are very confusing. It's a reference to the table, and then a bucket index in the table, and then a iterator into that bucket's singly linked list. So it's a very complex type, the hash table iterator. And the logic for traversing a hash table is non-trivial, let's say. It's kind of confusing. So this actually becomes much simpler now, which I love. So remove, what we want to do now is we want to, as we can assert that the iterator m bucket, just some sanity checks here because why not? Okay, and then can actually, let's see, auto bucket. We'll do this. Just make it a little nicer. So it should not be deleted and it should be used. Yeah, okay. And then, so we'll call the destructor, and then we'll minus the size and plus the deleted count. And then we'll mark the bucket used false, bucket deleted true. Yeah, that sounds about right. And then let's do something in our test here. So table remove the 3, and then we'll iterate the table again. And see how it fares. So we should get the same output followed by a new table without the 3. And it looks very good. Cool. So are we API compatible now? We're probably missing a bunch of things, like these things where we copy construct a hash table from another hash table. We can do that. Let's see. So that would be, I mean, it's essentially exactly the same code. So copy construct would be const hash table other, or mash table, sorry. Rehash other size, and then something like that. Because if you're doing a copy construct, there's no point in preserving the deleted entries of the other table. Like if the other table is full of deleted entries, we can just hash and get rid of those in our copy. There's no value in duplicating that state. In fact, the deleted entries are going to slow down your hash table a little bit, so you don't want to go too far with those. Because when you're traversing, you have to skip over them. So assignment operator. Actually, I mean, these are just the same. We can just copy these. So rehash and wait, what do we do differently? We don't have to do anything differently here. We have to update the other guy's deleted count. That's important. And the move assignment operator also has to take the other guy's stuff. So mbuckets is, let's use exchange. I like exchange. It's expressive. Okay, and maybe we should just API compatible here. And then we have this API. Don't remember who uses that, but we should be able to just take that in like that. And is that everything? I think maybe that's everything. Okay, let's see. So it compiles, it runs. FileGrind does not complain. It's very cool. So let's start by, let's see. Let me just copy these somewhere, just for safekeeping, just in case. And then we are gonna put the mash table, replace the hash table. With this, I guess we'll keep the old copyright here, actually. And then mash just becomes hash. Oof. Will it build? Nope. Oh, crap. Okay. Where do we start? We need a comparison operator. That's easy. In fact, they can just be like that. Redefinition of hash table. Did I forget to pragma once? Rookie mistake. Okay, and then the slot, we are not casting the slot correctly to a const type. That's true, I forgot. Oh. Somebody assumes that hash table brings in temporary change, it looks like. Well, you should not assume. Then you make an ass out of you and me. So shell cpp wants ack temp change. Okay, seems like he's not the only one making that assumption. Okay, a running theme is emerging. Memset was not declared in the scope. Okay, so let's just use the built-in memset, not deal with that. Maybe we can build test.js for the host. It's a quicker build. Because if that works, then we're good, basically. Oh. Oh, okay, we have a problem. Where are we crashing? In define property. Okay. Maybe we can build the hash map test. Fail. Cool. Okay, great. Case insensitive does not work. Case insensitive and line 88. So this, we're inserting something that should be a match, but it's not overwriting it. I guess we can. Okay, wait. What does this thing return? Hash map set returns the set result. Yeah. So we can even improve the test here. Say expect equal hash set result, inserted new entry, and this guy should be replaced. Okay, but that does not happen. Interesting. So hash table set is presumably doing something wrong. Okay. So the second set returns the correct result, but the table is busted. So we're setting something that already exists. So the bucket is used. So we're doing a replace. I guess we shouldn't be placement newing if the bucket is already used. Yeah. So we can maybe do it this way. Something like this. Otherwise, we'll placement new. Okay, I feel like that makes sense. Yeah, that was the problem. Okay, great. So let's see if that fixes the JavaScript test. Not quite, okay. So we're asserting, well, hold on, let me run the test hash map first. Yeah, right, so that one actually works. Wonder if the JSON tests work. They failed. But that probably has something to do with something else. Yeah, right, so they run. I guess we need to find out what happens with the JS test then. So the failure was in object define property, object put own property. And then it says that we are indexing outside the bounds of a vector. Sure. At object CPP 539. Here. Well, I guess I probably made some silly mistake somewhere, so let's see. Let's turn on the debugging here just to see what it's actually doing. Wait, that didn't print anything. Am I compiling this thing? Okay. I mean, maybe we didn't actually get there. Fine. Let me see then. Where is that? Right. Hello. Yes. And here we will print out the metadata value offset. I don't know, just something to see that we are on the same page. Okay, so we have a property at offset 7. And what is the storage capacity? Of this object. See, offset 7 into something with storage capacity 5, that's not going to work. So I wonder, have we been removing things from this thing? Did I not do removal correctly? That feels correct. Size goes down, deleted goes up. Uh-huh. Uh-huh. So let's just print out more stuff and see what's happening. So why do we have a property offset 7 in this thing? That seems incorrect. Let's just print out here what we're doing. So put own property. Put own property with this name. And maybe the value also. Do we have formatters for these things? Nope. To string without side effects, please. Okay, so we're putting a whole bunch of properties, blah, blah, blah. Let's see if we can do this a bit later. Is new property. Now we ended up debugging JavaScript here, but we're just trying to find out why this goes wrong. So JavaScript shapes or object shapes keep track of their property table in a hash map. So that's why we're here right now. So we're adding new properties. I guess maybe we should print out what object this is. So into Okay, so we're adding things to the same object. And after adding property offset 3, we suddenly jump to 7. Okay, so where are we adding properties? Presumably here. We do a set. Okay, so let's print out what the thing looks like after we've added something. Property table after add. Maybe just a name and the offset is interesting enough. So oh. Okay, so this is our table. We have 5 entries. This one has offset 7. So when we're adding nan to the global object, I guess, then it gets property offset 7. Why on earth does that happen? Property count. Wait. Who decides the offset? Add property without transition. Yeah. Okay, we'll log that here. How many properties he has before we add. Property count. So he has 0 properties. 1, 2, 3, 4. We're adding nan. Why do you get 7? That doesn't make any sense. Oh, wait, hold on. So we would be here because the global object has a unique shape. And we are using the property table size as the offset. And that comes from us, the size. So are we incrementing the size a little extra and so it gets to 7 for some reason? I'm guessing that we do. So let's print out the size of the property table. Property table size. It's probably going wrong somewhere. Property table size. size 7. Okay, so they're in sync here, 0, 1, 2, 3. But then it grows. After 4 entries, which is probably when we rehash the table. Yes, that makes sense, because when we rehash, then we iterate over the old buckets and call set. This will increment the size every time. So the size of the table grows when we rehash, even though it shouldn't. So what we can do here is we can say size is 0. If we have old buckets, then size is 0, and then we insert all of them. Yeah, I think that makes sense. So yeah, so the size was doubling when we rehashed the table. That was the whole problem. Or one of our problems anyway. And now we are stuck in lookup for writing. It's looping forever, okay. And why? So it keeps going around here forever because we never find an unused bucket. But there should definitely be an unused bucket. Well, let's just printf debug our way out of it. So and I would say your capacity. Yeah. Capacity, bucket used, and bucket deleted. So let's see why we get into an infinite loop here. Wait, it's not even looping. Wait, what? So what are you actually doing? Okay, so it does do that. Yeah. So we have a table with capacity 4, and all of the slots are used. Well, that's not supposed to happen. We should have grown the table before then. So when we added something, let's see. We should have grown the table. Why didn't we grow it? So the used bucket count at this point would be 4. We have 4 used. 4 plus 1 would be greater than capacity. And that would be 5 times 2. So we should have rehashed to 10. Why didn't we rehash to 10 when we added? I wonder if we're doing something stupid here. Well, we don't really have a test to test like a huge number of entries, many strings. I don't know, something simple like this, right? What if we just do this? just verify that this thing works. I guess that worked. Got a lot of output. We didn't get stuck. Here we can see also like how many iterations it takes sometimes, so how many double hashings you have to do. Maybe we, I don't know, should tweak the load factor at some point. Anyway, we're not gonna sit here and tune this thing now. I just wanna make it work. So what are we screwing up then? We have a table with, let's see what the size is. And let's see what the deleted count is too, actually. Oh shit, so many deleted. We have more deleted than capacity. That doesn't seem right. That makes it, that's not accurate. Are we screwing that up when we set here, rehash? When we rehash, we need to drop the deleted count as well. Yeah. Yeah, there we go. Okay, so now we just need to nuke all of the debug logging, which was actually not that much. Or maybe in libjs also. Here I can just spam Control-Z. Maybe keep that one. Okay, it runs. It's pretty slow, but it's probably because we turned off optimizations. So let's bring those back in. But yeah, so it we ran the whole JS test suite, passes all the tests, very good. Now we just want to run it again with optimizations enabled. And we can do some unrelated commit here in the meantime, because we had those instances of bringing in temporary change. JS, don't add, let's say add some missing temporary change includes. That's fine. And actually that test was kind of cute. Let me just add that. Improve hash map tests a little bit. All right. Moment of truth. This is reasonably fast. Wonder, let's see. So we have a new one, and hash table. I'm just gonna, just for safekeeping. So it runs in about 318, 330 something milliseconds. Compile the old version, see what that takes. Because I think it might be a bit slower. Yeah, it's a little bit slower. Okay, so let's just quickly see why. So now I'm profiling the original version, and then we will profile the new version. So the original version had what is that? 1.9 billion, 1.98 billion cycles. And the new one actually does fewer cycles, but still runs slower. So that's interesting. But we can probably get that down quite a bit. Let's just see what it is doing. If we look here, we see hash table is quite far up. Shorten templates, hash table set is heavy because wait, what am I looking at here? Oh, wait, this is looking at the outdated code. Shit. Okay, hash table set. Why are you so far up? What are you doing? Time is spent in kmalloc. Yeah, that's kind of unavoidable. And here, the rehash is. Wait, what is this? Yeah, rehash is expensive, of course. Wait, where are we spending all the time though? And why does it look so weird? Dang it, how did I... Wait, I don't want that. Now I've messed up my UI here. Oh, wait, I can just... I wanted to look at self. So hash table set is expensive, sure. Most of the time we're not setting on a deleted bucket, that's good. All these kmallocs, expensive. Sure. So I wonder why set is expensive. I guess lookup for writing. We'll do a lookup for reading. And then we'll look again. So let's just make this thing return a candidate. Let's see. Usable bucket for writing. So do that, and then if we find such a bucket, then we don't have to iterate again. Okay, and then we can skip iterating twice here if we can just forward this. So this goes here, this goes here, and then so the first bucket that we find that's not used, we'll store that here. Yeah, and then the caller can make use of that to avoid iterating again. No, that was not good. The usable bucket for writing, should it not be the first not used bucket that we encounter? Because that is the criteria later. So this is the iteration that we want to skip. We also, I mean, it's nice if we don't have to hash again. Wait, why doesn't this work? We get stuck. All right, well, that's good. We're stuck on a smaller test. Okay, so we can print out something. So we're finding some usable buckets. Wait, what am I doing wrong now? Deleted. Let's print out what this bucket looks like. Used, bucket deleted. I mean, it should be used false. On the index, we can put the index as well. So now we are stuck where exactly? We are stuck in this template. Oh my goodness, what are you? It's a lambda in lookup for reading. Wait, what? Why are we stuck? Are we looping? Let's see. Actually, this is not even where we are. We should be in lookup for reading. Or... no, it's the lambda. Okay, so we're here and we're calling this. Okay, so we're just going round, 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 round here. Cool. So what is the difference? If we find a usable bucket, if we didn't do this, then we would continue and potentially rehash. In our case, we will never rehash. But then we have, what is the situation here? Should I say size? DC, deleted count, and the capacity. What's going on? We're at capacity. Well, that shouldn't happen. Wait, how did we get to this point? Lookup for writing. Oh, wait. So now we'll, if we do this, then we'll never rehash. That's true. Okay, so we still need to rehash. If the size is getting too close to the capacity, we still have to rehash the table so that it grows, so that we always have empty space. Otherwise, the linked list will not work. So if we rehash, then we can't use the usable bucket, but if we don't rehash, we can use it. And then it works. Yeah. Okay. That makes sense. Okay, we are learning so much. Let's test this with test.js. And I'm running out of time now, so I'm gonna have to wrap this up, but let's just see that it works. .318, 311. Yeah, it's okay. So it still needs some tuning to be as fast as the old one. But I'm pretty happy with the new data structure part of it, like the fact that now it's a single allocation instead of many lists with tons of allocations. So I'm happy about that, but I'm going to need to spend some more time figuring out what's slowing it down and what can we do about that. But I don't have time to continue with that now, so I'm just going to wrap it up here. So if you made it this far, then I thank you for watching, for hanging out, and I hope you saw something interesting. It was a little bit of a different video today, working on data structures. I'm gonna wrap this up later, I think, but it's a decent point to end at because it works. It's just a little too slow. Anyway, thanks for hanging out, and I'll see you next time.